Hey, hi all, good morning.
Good morning, sir.
Morning.
Just a minute. All right, so yesterday we discussed about chi-square test and there we left. So we will continue with that. So before that, anybody has any question on other topics? Okay, so we will look at the mathematics around chi-square test and then we will get into Python. Okay, so let me we there is a small example which we will do it. Again, if you guys don't have pen and paper in front of you, just go and pick it up. So we will do it together. If you do it once, then it will stay in your mind, guys. So better, you do it along with me. All right. So here is the table. All right. So this example is all about a particular application or website where people are kind of coming and subscribing or they are registering for certain things, right? So here the data is something like this. So we have subscription. Let me change the color. So we have subscription and non-subscription people, okay, who have not subscribed and subscribed. So here there is some customer or the user segmentation has been done, which is also a categorical variable. So here we have low income group, then we have medium income group, then we have high income group. Okay. So overall, there are around 140 users. Okay. So now the breakup goes like this. Sorry about my handwriting, guys. Low income out of low income. So there are around 50 total low income people, and 65 are medium income, and 25 are high income. So overall, we have 140 users. Okay. Now, this is the breakup 20, 30, 40, 25, 10, 15. Okay. Now, this is sum is 70. So equally, people have subscribed or not subscribed. Now, so in every, so we have around three population here. Okay, low income group, medium income, or high income. So the proportion of subscription in the low income group is 20 by 50. So that's your P1 hat, right? Medium income is equal to for subscription it is 40 by 65. Then high is it is 10 by 25. So here we are talking about three samples: P1 hat, P2 hat, and P3 hat. And now by looking at it, so it's almost like kind of close to 50%. right? In each of these populations for low income, medium income, and high income for subscription. Now we have to statistically check that whether these are equal or these are not equal. So that's where we are going to use the chi-square test. And here, if you see, these are all proportion. This is not, these are the count of people. Okay, because of the count of users, we can able to calculate the proportion of that particular segment in that particular of subscription in that particular segment. Now, we know about, so have you noted down this part? Okay. If not, then take a minute and just note it down. So yesterday we discussed about a formula, okay, which is I equal to 1 to n O minus C. It is expected square by expected. Okay, so that is the formula for the chi-square. So this is something, okay, we are going to see how we can calculate the expected, what is the observed, and how can we calculate the test statistics. Okay, so now let's go and find out the expected score. Okay, so I hope you have noted it down. So let's move to second slide. So here I will just take a uh, one single example to calculate how we basically calculate the estimated. Okay, sorry, the chi-square test, and for that how we calculate the estimated calculated score. Okay, first, you can call it as estimated or sometimes it is called as calculated. Okay, so that we will discuss. So for that, the formula is, just a second, guys, somebody is pinging me. Okay, sorry about it. Okay, so we know the formula of chi-square is I equal to 1 to n, and it is O minus C or E. Sometimes in some of the books it is called as calculated score, some of the books it is called as estimated score. So for now, let's put it as estimated by E. So this is the formula. Okay, so now in our table, okay, we have the row total and we have the column total, right? So for every single row, like low income, medium, and your high, we will calculate the expected score. Okay, so the expected score formula is row total into column total divided by grand total. Okay. So for example, for low, if we have to calculate, let's see. So what is the row total? It's 50. What is the column total? It is 70. And what is the grand total? It is 140. So it would be 50 into 70 by 140. That is for low income. So for the low income, 50 into 70 divided by 140. What would be for medium? It is 65 into 70 into 140. 65 into 40 by 140. And for high, it is 25 into 70. 25 into 70 into 140. This is 70 only. 1 second. 25 into 70, right? So this would be also 70. I'm sorry. This was subscription, right? So these are the row total for low, medium, and high. The 70 is the total for subscription, and this 140 is the overall grand total. So with this, we can able to calculate this score E. Okay, which is for this it is 25. You can calculate for this what it is. Okay, so meanwhile, I will just draw a table. So here this is expected score what we are calculating for subscription. So similarly, we have to calculate the expected score for not subscription also. Okay, so you can calculate. So whatever would be our interest to measure the proportion, whether it is a subscription or not subscription, I'll consider that expected score for calculating my chi-square. So here in this case, my interest is only subscription, so I have calculated the expected score for subscription. Okay. Okay. So now I will go and now create a table. So this is my subscription. This is I measured as O, and this is for subscription. I will put it as E. Okay. For low, for medium, and for high. Okay. So for subscribed, it is the number is 20. This is 40. This is 10. Right. So this is the number 20, 40, 10. So this is my observed. Observed means this is I made the experiment, I conducted the experiment, and this is what I observed in my sample. Like out of 50 low income, 20 people have subscribed. So that is my observed. Now here it is my calculated or expected score, which is coming out to be as 25 for low. Anybody has calculated for medium what it is? So it is 35, it is 10. Okay, so now you have observed, now you have expected. Now with this, I will go and calculate the chi-square value for each of these subscription. Okay, so now this would be 20 minus 25 whole square divided by 25. So it is O minus E whole square divided by E. Okay, and this would be 40 minus 35 whole square divided by 35. This would be 10 minus this will come out via 0. Okay. And similarly, I will go and calculate for non-subscription also. So take it as an exercise and do it for non-subscription also. Okay. Now I want to find out. Now what I will do is I will find out for non-subscription also. So there would be another 3 terms, and then I will add it. Okay. So the total value would be your test statistics, which is come out to be as 3.747. You guys can check. Okay, you do it at your end and you can check. And now degrees of freedom. Degrees of freedom would be a row count minus 1 and the column count minus 1. So it would be 3 minus 1 into 2 minus 1, which will be equal to 2. Are you following, everyone?
Yes.
Okay, so degrees of freedom is this. So now you take this test statistics at this degrees of freedom and you follow the chi distribution. And with that chi distribution, you can find out the probability. That would be your p-value and that you compare with your alpha. So you need not to worry about all this calculation. This is just, for your understanding. I explained you. This is one example. See, but what we are doing here. So with this chi-square, what exactly we are able to conclude? Here we are concluding that this subscription, whether the person user is subscribing or not subscribing for your application or on your website, is it is it is it influenced by the segment, customer segment, or is it not influenced or not impacted or affected by the income of the user? So if we get a conclusion that these all proportions are not same, that means the income group or the income is impacting the subscription part. So then later you can go and do the two sample test to see which kind of income group are subscribing more to your application or to your website. Okay. And then accordingly you can plan your campaigns, you can focus in that particular area and you can take a strategic call. For example, if the low income group are subscribing more, then again, it's you have to take a call, whether you will get better revenue, you cannot, right? So you have to change the business model so that the medium income people or the high income people should subscribe more. Okay, so that your revenue would increase. So so this can be used for strategic decision. And the second is like machine learning. During the machine learning, again for variable selection, we will use it just like the way we have seen in ANOVA. So ANOVA helps us in choosing the uh, uh, appropriate or choosing the significant columns which is impacting your continuous variable. Here, for the classification problem, this chi-square test will help us to choose a significant categorical variables. Okay, if I have to build a classification model, I have to predict whether a particular user will subscribe or not subscribe. If that is my predictive model, then for I will select the columns which are significant, okay, which are kind of driving this subscription. So for that, I will go and conduct this chi-square test, and then based on the hypothesis testing, I will conclude whether that particular variable is significant or not. If the null hypothesis is coming out to be true, then I will not select this particular column. Now, in that case, all the income groups, they are going and subscribing, then that means there is no impact of this uh, customer group on your subscription. Okay, so that's how the ANOVA and the chi-square test are used for two purposes. One is for strategic decision and second for machine learning purpose. All right, so now we will quickly get into the Python code. So any questions so far? All right. Now in the real scenario, you will get different kinds of data sets and you will get different kinds of problems. So today we'll see that how you can solve those kind of problems by using Python. Okay, if it is related to hypothesis testing. So for example, in this case, I have this data. So I have a huge data set. Let's suppose this is a patient data in which I just selected these few columns. So I have a patient number, I have a patient gender, age group, BP before and BP after. Okay. So here I can perform various tests. Okay. I can perform the chi-square test between the patient gender and the age group. I can do it, if there are no more than two groups, then I can do a two sample test. If it's more than two, then I will go with the chi-square test. Okay, and here we have a BP before and BP after. So this you can consider it as a paired t-test. That also I can perform. If I have something available population information, then I can also perform one sample test. So sometimes it is not very clear like what kind of test you have to perform in that. So in those cases, in those scenarios, looking at the data, you can perform multiple tests and you can give it to the business saying that based on all these different tests, this is what is the conclusion, and then let them decide, which hypothesis testing they would like to go to. So for example, now this is my data where I have a lot of patients and their gender information, age group information, and their blood pressure before the treatment and after the treatment. Now let's just consider these two columns, and I said describe, so I will get some information about the summary about these two columns, like what is the count, what is the mean, standard deviation. So basically, this is my sample. So I have only 19 observations in this particular sample. So here I cannot go and do the proportion test because the gender and the age group are constant. It is not changing. So there is no different categories in this. So I will just pick up only one column and let me go ahead with the one sample test. So in the one sample test, for one sample test, you go. So I prefer this. There are multiple other packages are also available in Python. So go with the stats models dot stats, and in that import weight stats, and then I put a small name as S tests. S tests. Okay. So this is basically the path where you will go and you can find out the Z test. Okay. So So it's a folder kind of a structure in Python. So you will have a one main folder which will act as a library or the package. Inside that you will find multiple different modules. Inside the modules you will find multiple different methods. So here stats model is the package, then stats is the module, and then in that there is a method, and in that there is a function known as STS. So that's how you have to call a particular function. Okay, you import it, and in that particular function, there is a method known as ztest. Okay. So I'm just passing this ztest in this data frame, whatever the data, I'm passing that particular column. And here it is a numerical column, patient's BP before. I'm passing only just one column. This particular test can be done on two samples also, but in the second sample, I'm calling it as none. So x2 is equal to none. X1 is this. And here I have some information about the population mean. So here the value is 146. So I'm passing it here. So one sample is what where you have some information about the population mean, and then you can go ahead and perform the one sample test. So here I'm passing that population mean 146. So it is the average BP what they are considering that the people whoever come to the hospital, this is the average BP, and I'm going and checking that in with my sample. Okay, so I perform this test, and for one sample, guys, there is no straightforward, I would say, approach for lower one tail test for one sample. So by default, it does the uh, two tail test. Okay. So what I said again, I'll repeat. For this particular function, there is no straightforward approach for doing the one tail test. So here by default, it is a two tail test. Now, if you want to convert that into a one tail, we will see that how we can do it. So here it is dot z test. Here I'm passing one sample. Okay, the second sample is none. I have to compare with the pseudo population mean. Okay, now when you run this, you will get two values. One, you will get test statistics, another, you will get probability. Okay. So these are the two values. The test statistics is minus 1.410, and the probability value is this 0.1584. Now, once you get the probability value, okay, now you have to go and check, compare with the alpha value. Here, alpha value by default, I'm taking it as 0.05. If it is less than 0.05, the null hypothesis is rejected and alternate hypothesis is accepted. Okay, H naught is rejected. Else, the null hypothesis is accepted. So as it is greater than 0.05, now it's saying that null hypothesis is accepted. So this is basically a two-tail test. Okay. Now if you see, and just add one. If I run this, See, now when I'm running this PDF to calculate the probability of this particular test statistics, it is showing as 0.07923. So if you multiply with 2, sorry, then you are getting this particular value. Generally, when we multiply by 2, the probability value when we are doing a two-tailed test. So that's how, we have seen that, okay, by not putting anything by default, it will do the two-tailed test. Now, if you want to do the one-tailed test, just directly, calculate this Z test from this particular function and then use the probability, and just instead of, putting this as a logic as a condition, you can put the condition on this part. So this is what is the lower tail test. So I'm getting the probability as 0.158. Okay, so that probability I will test it with 0.05. And then if it is less than the hypothesis is rejected, null hypothesis, otherwise it is accepted. Okay, so at the lower tail test also, it is saying that we should accept the null hypothesis. Okay. So what is the null hypothesis? Null hypothesis here in this two-tailed test, it says that the mean of the uh, patients, the mean blood pressure of the patients is equal to 146. And the alternate hypothesis is saying it is not equal to 146. Okay, and we are accepting the null hypothesis that it is equal to 146. And in this lower tail, we are null hypothesis, whatever we are accepting is that this population mean is greater than or equal to 146. Okay. All right. So stop me, guys, wherever you have any questions.
Yeah, here
Yeah.
the stats norm.cdf is same as the population mean probability value, which is on top.
Yeah. This is right. This is the test.
The probability value is same, right, for both the.
No, 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 no. So here the probability value for the two-tail test is
Mhm.
whatever you are getting out of this distribution at this particular uh, z value, you are multiplying it with 2. Okay.
Okay.
Okay. So this is what you are getting 0.0792 at this particular z value.
Mhm.
In the two-tail test, if you remember, what we do is we multiply that particular probability by 2 to compare with the alpha. You
Mhm.
remember or you forgot?
Forgot.
Forgot. We discussed about this, right? This is alpha by 2, this is alpha by 2.
But
So whatever probability value we will get, either we compare with alpha by 2 or else we multiply that probability value with 2, then that will give me the p value. And that p value will compare with alpha value. So that's what we have done it here. Okay. So usually what we are getting is, this is the probability value, 0.0792368. This is multiplied by 2, in this particular case. So by default, if this will give me the two-tail test. So internally only it is multiplying the probability by 2 and then giving us the p-value. Now this is my p-value for two-tail
Mhm.
test, 0.158. Now this will be compared with the alpha value, which is this 0.05. And based on that, the null hypothesis is accepted or rejected. Now let's suppose if if you are doing the lower tail test, now the entire alpha is here only, right? Now, whatever probability value you will get, that would be your p-value. In that case, you directly go and compare with the alpha value. That's what I have done it here. So here the 0.0792 will be compared with 0.05.
Right. Okay.
Okay.
Yeah.
So now moving down. So let me share my screen again. Okay. So Yeah, so here I'm randomly generating certain samples. So in some of the scenarios, you will not have a data with you and you have to simulate the data. And we have seen, right, we have lot of probability distribution functions available in NumPy package, which we can use, generate or to simulate some values. Okay. So here we are using random function from NumPy, which will randomly generate certain number. And then we are also using stats to randomly generate certain numbers, from the uniform distribution. So so what we are doing is, if I have to explain, but you need not to worry about, if you don't understand. So this is something I've used, to generate this sample. So whenever you are generating any number, okay, from a random probability distribution, if you set a particular number to it, that this RNG, so I'll show you. Okay, so this is a generator. Okay, it will randomly generate certain values. So that generator, I'm putting it here in the random state, okay, to generate some samples of size 50 from this uniform distribution. Okay, that's what I'm doing. If I'm running this, it is randomly generating certain number for me. Okay, every time if I run, if you see, you will find different numbers are getting generated. Okay, so or else what you can do is you can ignore this just to avoid any confusion and put a number here, random state. So if you put a number, if you change the number, so just remember this first number. It is 0.7713, right? And the last number is 0.165. So just remember this number. I'm changing this random state to 9. Numbers have changed. Again, I'm going and changing it back to 10. See, again, I can able to regenerate the same numbers. So first number is 0.77 and 0.65. So that's how the random state will help us to generate the same sample again. So from the same distribution, it will pick up the same values. So if you're sharing the code to somebody, if you don't set the random state certain number, so he may get a different sample, and whatever you got from your analysis would be different than what he will get. Right, so right like that, I'm randomly generating certain numbers. So this we call as a Monte Carlo simulations. If you do not have any data for sampling, you can use this probability distributions to generate certain samples, and based on that, you can perform your hypothesis testing. Now, this is my sample. I do not have any information about anything else. Okay, so there I will go and I can perform the t-test. So here, see, the now t-test can be done in two ways. One is like if you have a population mean given, but if your sample size is less than 30, then you cannot perform the z-test. Okay, this is something I haven't told you. Minimum to when you are using any z-test, minimum sample size has to be 30. If it is below 30, then you have to go and do a t-test only. Okay. So here I'm going and doing this t-test. So from SciPy, I'm importing this particular module stats.t-test underscore one sample. Okay. So this would be your function which you have to use to perform this one sample t-test. So automatically in the backend, it will go and calculate the degrees of freedom, everything. Okay. So I'm going and doing this. So it is giving me the test statistics. It is giving me the p-value, and it is giving me the degrees of freedom. Okay. So by default, it is giving you the two-tail test. Okay. Now, if you want to perform one tail test, then there is an option here in this function. You can mention the alternative. If you can mention the alternative as greater or lower. If it is lower, then that means you want to do a lower tail test. If it is greater, then it will do upper tail test. So again, guys, so these are the functions which will give you the numerical output. Okay, that you have to convert that into a proper conclusion. So that, so for that you have, you either you can write the uh, if else condition like this. Whatever numerical output you are getting out of this function, then you compare with the alpha value and then print a statement like this or your proper conclusion. The way we have seen on the slides, like we do not have enough evidence to support that this null hypothesis is correct or alternate. So like that, you can write the statement here for just, in short, I have just written as null hypothesis rejected or alternate hypothesis accepted. But if you are putting that into some application or you want to generate a report out of it, then you can mention the complete sentence. Okay. Any questions?
Yes. So the random values which you're generating, so wouldn't that spoil our like calculations? In the previous example where you said the BP,
So,
let's say.
yeah. See, one is like from the real world, you go and pick the sample, right? If the data is available.
Mhm.
I'm saying if what if the data is not available? You just know the property of that distribution of that data. So you know that this particular column follows a uniform distribution within a range of this 10 to 20. If you know that much information about the data, now you can use a simulation technique, to simulate the data. And this is generally done in multiple scenarios where you will not have the actual data, but you want to do some kind of a simulations. If you have some idea about the distribution, you will do the simulation, and based on that, you make a decision. Then accordingly, you set up the process in that way. Okay. So we have discussed that in the probability distribution classes, right? So where we discuss that these particular distributions are meant for two purposes. One is like to calculate the probability, and that's what we are doing, right? We are referring to the Z distribution, T distribution, and based on those test statistics, we are calculating the probability value from those distributions. That is one. Second, I mentioned at that time that these distributions, if you know the characteristics or the parameters of those distribution, you can use it for simulation. Okay.
Yes.
Any other questions? It's okay, guys, if you are getting any question, get it clarified. Okay, so we will continue. So, for example, now I do not have the population mean. So, what I will do is I can go and use the sample mean. I'll say np dot mean, and I will pass this particular variable RVS. Okay, so it is giving me this statistics is 0, p value is 0.5, and degrees of freedom is equal to 49. Okay. So now it is rounding it to one decimal place. So that means the test statistics is very, very small and the p-value is coming out to be 0.5. Okay, so based on this, like this, you can do the one sample test. Is it clear? So just you need to pass the sample and you need to pass the mean. That's all. And it will give you the statistics. And see, in the real data, it's like a table, right? And you can pass any column. So for example, now I will perform this on this particular column, like whatever column we have here, right? BP before, right? We'll take this particular column and we'll perform the t-test. Okay, and let's take certain value. Let's take the mean of this one, right? 141 plus 141 here. So degrees of freedom is 18. Okay, and p-value is coming out to be 0.944. Okay, with that, we cannot reject the null hypothesis and we have to go with the null hypothesis only. We cannot reject it. So in that way, you can just take the data, whatever data is available. Either you can read the data from database or else you can read the data from Excel on whatever column you want to perform these hypothesis testing. You just select that particular column and then pass it to this function. Okay. So I'm just giving you a real scenario. So you have a data, you have imported that data, and then you are from that particular data, you are reading a one specific column and then performing your test. Okay, and based on these results, you can conclude whether you have to go with uh, null hypothesis or you have to go with the alternate hypothesis. Okay. So let me show you one more thing. Now you can use this stats.t.cdf. Before we have for this particular for Z distribution, we have used this norm.cdf, and for T distribution to calculate the probabilities, we will use t.cdf. Okay, so I'm passing this particular value here. And what else we need to calculate the probability from the T distribution? We need the T score and we need the degrees of freedom. So degrees of freedom, I'm passing it as 18. So now here the value is coming out to be 0.47. As I mentioned, if you do not pass anything, any argument in this particular function, by default, it will do the two-tailed test. Now I'll just multiply this particular part with 2. I should get this particular value, p-value, which is in 0.94456. So this is how, it's proved that this particular function, by default, it is doing the two-tailed test. With a two-tailed test, my hypothesis should be equal to or not equal to. If I have to do a lower tail test, then I can go and put a alternative like lower. Otherwise, if I want to make the upper tail test, then I'll put a alternative as greater. Okay. So I hope it's clear. So that's about one sample mean test. In one sample mean test, if you refer to the flowchart yesterday, what we have created, we have two options. One is like where the sigma is known. And sigma is known, then we have to go and perform the Z test. If sigma is not known, is unknown, then we will go and perform the T test. Okay. So this is about the Z test and the T test. Now we will see about the proportion test. Now in the proportion test, let's suppose this is my value. This is my capital P, which is given to me, and this is my sample. Number of sample observations in my sample is 83, and in that only 5 observations are of my interest. So that means 5 by 83 I have to compare with 0.01. Okay, so this is my problem. Whether whatever proportion I'm getting from my sample, whether that is equal to my pseudo population proportion, which is 0.01. I have to compare with the given population proportion. And based on that, uh, I have to either accept or I have to reject the null hypothesis. So from again stats module dot stats dot proportion, I'm importing this particular function known as proportion underscore z test. And in that, I'm passing out the count, which is the number of objects of my interest, and the sample size, which is n observations. And this is the population proportion, which is value. I'm passing this, I'm getting this Z test, and I'm getting this p value. And based on this p value, I will conclude whether the proportions are equal or not equal. All right. Any questions? So this also you can validate by using z norm.cdf to see whether you are getting a right probability at this particular Z test or not, okay, test statistics or not. So it's one line of code, guys, for every sample test. You just need to pass the right parameters and you have to read the output correctly. So if there is nothing mentioned in the parameter as alternative as lower or greater, in that case, you have to by default consider it as a two-tail test. If you want to perform a one-tail test, then either you have to explicitly go and mention that alternative is equal to lower or alternative is equal to greater, or else whatever values you will get out of this particular two-tailed test that you have to divide by 2, to find out the one-tailed probability value. Okay, now we'll proceed on the two sample test. So in two sample test, let's suppose these are my two samples. Okay, these are independent samples. Again, in the two sample test, if you refer to that flow chart, so there are two cases. One is independent samples and the second is the dependent samples. So for the independent samples, we use this particular function t-test underscore independent. And in that independent sample, again, we had two scenarios, right? Variance are equal or variance are not equal. If the variances are equal, then by default, it will be marked as true, or else you have to explicitly mention it as false. So here, let's suppose I'm going for unequal variances. Now I'm passing these two samples. That's what you have to do. And it will give you the test statistic, the p-value, and the degrees of freedom. And for each degrees of freedom, what is the formula for test statistics? What is the formula? We kind of looked into it, right, in our previous classes. You can refer to that. Okay, if I am assuming that the variances are equal, just I have to mark it as true, and it will give me the t-test, okay, which we call as a pooled t-test. So this is the output of the pooled t-test. Now, finally, if I'm talking about the dependent samples, I will use this t-test underscore rel, okay, relative. So this will give me the pair t-test. Okay, so now what you can do is, you can take it as an exercise that this particular patient BP before and patient BP after, take it as a two sample and then perform this t-test relative to see whether that treatment is effective or not effective. Okay, you formulate the hypothesis accordingly, whatever you want to prove, and then accordingly you go and run this test and then uh, get the inference out of it. Okay, now we are going to two sample proportion test. In two sample proportion test, this is your own custom function which you can develop based on the complex formula what we have seen. You can define your own function and then you can use that function, to calculate the uh, test statistics and the probability. Or else you can go and use this proportion Z test which we have seen just above. Okay, and we can use this and we can perform the same test. So here I have two, instead of earlier we had only one count and one number of observations. Now here we have two counts and two observations. And this is the same example what we have discussed in the class, right? It is about, what was this about, 27 and 19, if I am not wrong. This was, I think, related to the paints use case, right? So they have taken 200 specimens. On the 100 specimens, they have applied one type of paint, and the another 100 specimens, they have applied another kind of paint, and they have measured the drying time. So here, for one sample of which size 100, 27, no, this is not that. What was this use case? 27 and 19, I'm forgetting. So you can check, guys. Okay, so 27. Yeah, this was that uh, medicine one, the placebo and the St. John Wort one. Okay, so which medicine is more effective? So 27 out of 100 patients have shown improvement when they have gone with one particular kind of medicine, that person's St. John Wort's medicine, and the 19 people have shown improvement when from the placebo. Okay, so that it is that particular use case. So I'm passing these two samples, first the count and then the sample size. and I'm passing it to this proportion test, and I'm getting the Z test and the p-value. Based on this p-value as it is greater than 0.05, I cannot reject the null hypothesis, and the null hypothesis states that the two medicines are quite similar. Okay. All right. So now this is your proportion test. Now we will go and talk about more than two sample tests. First is ANOVA. ANOVA we discussed yesterday. I think it would be fresh in your mind. So we have created that whole table where we have first calculated where we have divided the two sources. One is between the group and second was within the group. For the between the group, we have calculated the sum of squared, and then we calculate the degrees of freedom, and then we calculated the variance. Variance is nothing but sum of squared divided by degrees of freedom. Okay, so like that, we have calculated the variance for between group and we have calculated the variance for within group. And the ratio of these two variances is nothing but your F test, which is your test statistics for ANOVA. And that test statistics, we will go and uh, use it in the F distribution to calculate the probability value. So that probability value will be a p-value at which we will use, to compare with the alpha value. So here we'll see how we can do that. Now in the scipy.stat, we have another function known as f. So we have seen norm, we have seen t. Now this is a new function, new distribution known as f. So PPF will give you the value and the CDF will give you the basically the probability that we have already discussed in the probability classes. And here we will pass two different degrees of freedoms. In the F distribution, yesterday we have seen, right, in OVA, we use 2 degrees of freedom instead of 1. So here, if you pass these 2 degrees of freedom to this particular function, it will give you the F score, okay, for a particular probability. So now let's take an example. Now let's suppose these are my two samples. I can directly calculate the variance, okay, of these two sample and then find out the degrees of freedom. And based on that, I can find out the p-value or the probability value by passing this variance, this test statistics, which is nothing but the ratio of these variance and the degrees of freedom. Now, let's look at the ANOVA. I have these three samples. I've taken a very small example where I have only 3 observations in each sample. Okay, the sample size is only 3. So here, if you have more like that, you can have multiple samples. You can have 10, 20, whatever number of samples you have. You can have that many number of samples. And we will use here one-way ANOVA. There is a two-way ANOVA also, but as I mentioned, it is much more advanced topic and very rarely used in the practical scenario. So I will say stats dot f underscore one way. That's all I have to do. And I will pass these three samples. Now this will give me the test statistics and the probability. So by now you have observed that for every test, we are getting two values. One is the test statistics, one is the p-value. Now, you can use this test statistics and you can go and use any distribution function, to calculate the probability value. Okay. To cross-check whether this p-value is coming out to be correct or not. So by default, usually it comes correct until unless you don't pass the values or the parameters incorrectly. So now the statistics is 1.5 and the p-value is 1.296. So here there is no one tail. Okay, so it is only one single kind of test which you can do it in ANOVA, and where we will have only one hypothesis where the null hypothesis states that the mean of all these samples are same, and your alternate hypothesis says that they are not same. So here the p-value is greater than alpha, so we will conclude that it is same. We will go with null hypothesis. We cannot reject the null hypothesis. Okay, so that's how you can read this particular output. Now let's take a kind of data. Okay, I'll show you the data. The same data, either you can create a data frame manually. So, but what I did is I show you what I've done. So this is my small data set, okay? In each of these samples, I have only three observations. Now, let's understand what is this use case is all about. So here, in any school, I want to, they want to test whether the blackboard is more effective or the case presentation way of teaching is more effective, or using PowerPoint presentation is more effective, more effective. So what they have done is, they have taken multiple observations, uh, and they have tested on various people, and they have measured some score. For this particular person, he has given a score 4 on the blackboard and the case presentation 2 and PPT 2. Okay. So for him, the blackboard is more effective. For this guy, case presentation is more effective, and followed with blackboard and then PPT. For this guy, case presentation is more effective, followed by PPT and then black. So like that, I have all the entire data, and I will have a sample for each of these population. Now, overall, if just a generic statement, if we have to pass that, okay, the blackboard is better than all, okay, or else you say that you want to say that all the three medium of teaching are same. Okay, so there's nothing different. So here in this ANOVA, one-way ANOVA, we'll make that statement. We are saying first the null hypothesis says that all the medium of teaching is the same, whether it's a blackboard or the case presentation or the PPT. So my alternate hypothesis is that these are not same. They are not effective in the same way. So here I have this data. What I did is I collected this data, okay, and then I save that data in Excel, and that Excel I'm loading that into Python. I'm reading that data. Now I'll do some kind of a preparation, data preparation. I cannot feed the data just like this. Okay, it is in the form of table where the samples are each columns. So I will make certain changes to this particular table so that I can feed it to my function, to my one-way ANOVA function. So for that, let's see, what I'm doing. So here I'm adding one more column to this particular data frame as index. So this df.index, if you use, so it will give you this values, this index values. These are not columns, these are row indexes. One second, Gaurav. Okay, so here the df.index is these row indexes like 0, 1, and 2. This is not the column. I'm converting this indices as a column. Okay, so if I go and print this, now I got one more column like as index. So this I have added. Now why I have added? Okay, now if I show you the column names, so I have Blackboard, case presentation, PPT, and index also. Now these are my different columns. Now what I'm doing is now I'm reshaping this entire data. So see how I'm doing. So here whatever was my column names, I converted that into a category. So the first index as 0, if there was a blackboard value, there was a case presentation value, and there was a PPT value. So it has created one observation for blackboard. So these all columns has become a category now. 0, blackboard 4, 0, PPT 2. Then you will have one more like 0, case presentation 2, right? So I reshape the data like this. So now I want to see that on this particular value, is this particular variable is significant or not. So that means the impact of each of these teaching medium is different or not. Okay. So if I want to predict the output of the teaching, then is this particular information is important for me to consider or not. That's something I will go and test with ANOVA. Okay. So for that, let me change the value, rename the column names. Okay, because this variable is not making any sense. So I've made it as treatments. Okay, and the value. So these are all different teaching treatments. Okay, various methods. Okay, instead of treatments, let me put this method. That is more. Okay, so these are the different method and these are the value coming out of this method. Okay, so now I want to see whether this particular method is significant to predict the value or not. Okay, so this we will see. We will talk about in the regression class. Just to give you a little bit of idea about how this ANOVA works, I wanted to show you here. OLS means ordinary least squared method. Basically, we use it to for regression analysis. So if I'm running this regression analysis, in the regression, if you see there is a F statistics. This is nothing but your test statistics score, okay, which is coming out to be 1.5, and will also give you the probability value at this particular test score, which is 0.296. If this particular value is less than 0.05, then that means these null hypothesis, uh, if it is less than 0.05, then you can reject the null hypothesis and you can accept the alternate hypothesis, which states that this method is significant. Now, in this case, as the probability value is greater than 0.05, here I cannot say that this particular channel or method is significant in terms of generating the value. Okay. So, and this is how the regression model, predictive model is created. So you will have the intercept, you will have the coefficients. This we'll discuss in regression. Just I wanted to bring it here, saying that if you want to build a predictive model, so this ANOVA is one of the measure. ANOVA statistics is one of the measure which you have to consider and analyze to to decide whether this regression model is a good model or not. Okay, for prediction. So now let's get back. Okay. Now the same model I will use and generate the ANOVA table out of that model. So I will use the sm.stats.anova underscore lm. And lm means linear model. And I will pass the model and I will put it as type equal to 1. 1 means one way. So this ANOVA table is created. Now this is the same kind of a table which we have generated yesterday. Okay. This is the degrees of freedom. Okay. And uh, this is treatment. This is for between group. Okay. Within group is they have not given. They have given the total. Okay. But if you see, this is sum of square they have calculated, and mean of square they have calculated. For within group, they have not shown it here. So you will have one more number here. I think this is within group only, residuals. This is not total. Yeah, for within group, second, how many observations are there? 6. Total is 8. Yeah, perfect. So this 8, n minus k is my within group, right? So n is 8, k is two groups, two samples. So 8 minus 9 minus, sorry, it's 9. 9 minus 3 is your 6. There are three samples, right? Blackboard, case presentation, and PPT. So k equal to 3. The total sum of all the samples is equal to 9. So 9 minus 3 is equal to 6. So this is degrees of freedom is 6. For within group sum of squared, it is 12. Mean sum of squared is 12 by 6. It is 2. The ratio of these two, 3 by 2, is equal to 1.5. And 1.5, if you go and look in F distribution, this is the probability what you will get. And the same values you will see that we are getting in this particular predictive model output also. 1.5 and 0.296. So this is a connection which I want to draw that, okay, these tests are also used in machine learning algorithms, right? Now this is some more example, like let's suppose you have these four samples. So through graphs also you can compare and see that all these samples are same or not. So this is a box plot. With this you can able to understand what is the distribution of each of the samples, right? and you can make some conclusion, or else you can go with ANOVA test and you can find out, how the distribution is, okay, how they are related to each other. Now, finally, the chi-square test, which we have discussed today. Let's suppose this is my data. I have age intervals and the experience intervals. So these two are the categorical columns. Okay. With this categorical columns, I will go and construct the contingency table. So the data will be in this form, but I have to do some kind of preparation of the data so that I can feed directly to my chi-square function. So I'm creating a cross tab, which is also called as contingency table, where I'm passing these two categorical columns and I will get the count. So just now in the exercise, what we have seen today about the subscription and not subscription and the low, medium, and high categories. So here in the rows are these categories and the columns are these categories. So these are two categorical columns on which, I have generated this particular contingency table. Okay. And now I want to see whether these two categories have any impact on each other or not. So from scipy.stats, I will use this particular function chi-square underscore contingency, and I will pass this data. Sorry. I'll pass this contingency. So I'll get the p-value. And based on the p-value, I'm taking the decision whether I should reject the null hypothesis or I should hold null hypothesis as true. So now based on this p-value, as it is very small than 0.05, I'm rejecting the null hypothesis. So this e minus 140 means 10 raised to the power minus 140. So this is as small as that. Okay. So it's showing that this is very small value, p-value, and as it is less than alpha value, I'm rejecting the null hypothesis. Or else, if you have some data in hand, okay, so if you have the count of the proportion for each of the groups, then you can directly pass this data also, and you can run it like this also. So in practical scenario, you will get the Excel sheets like this. Okay, you load that Excel sheet and then convert that into a contingency table and then pass that contingency table here in this particular function to calculate the test statistics and the probability value. Any question, guys? Contingency. Okay, so well, I'll share this code. Go through step by step, okay, every function in detail and run it, play with it, change the parameters, see what kind of output you're getting. Okay, take the same data and perform different tests. So all that thing, you do in that way only you will able to understand, how this functions can be used, okay, in Python. So do that practice, and I've also shared a couple of exercises related to one sample on the Telegram channel. Go through that as well, okay, and try to solve that. Use Python as a tool to solve those problems. So in that way, you will get a good hands-on understanding of on this particular Python functions. So I'll stop here. So with this, our hypothesis testing is completed, and tomorrow we will talk about correlation analysis and then covariances, and we will touch the regression. And then we'll get into linear model building and all those things. We'll get into predictive analytics. So by tomorrow, we'll be done with the diagnostic analytics, which we also call as inferential analytics. Okay, so initially we talked about some basic statistics that comes under descriptive analytics. Okay, we described the data, all that thing we have done. Then we moved into diagnostic analytics, where we are doing all this kind of tests to prove which hypothesis is true, okay, which one to reject, which one to accept. So with that, we will be done with diagnostic analytics. And once we get into regression, so at that moment, we will get into predictive analytics. Okay.
Okay, sir.
All right. So any comments, any guys, any things? I know that it is confusing, so it may take time. So for me, to clarify all these concepts, I took a lot of time. I took several months because I refer to multiple books. So that's the reason I am asking you to avoid referring to multiple books. So when I started studying this statistics, at that time, I thought I will go through multiple books. I purchased multiple books, but eventually I got confused and I didn't get it. So all the concepts were half cleared in my mind. Okay. So, but later, uh, through continuous learning and then through certain courses and all, those concepts got clear. So it took, good amount of time for me, to understand this whole hypothesis testing. Okay. So for you also go slow, don't hurry. Okay. And that's the reason I'm saying, put a notes, clear notes, saying that, okay, the flow chart, what we have discussed, right? And you can continue in continuation to that flow chart. You can mention that for this particular test, this function needs to be used in Python. For this kind of test, this function needs to be used. And accordingly, you will understand that what are the different functions are available in Python, what are the different packages are available in Python, and you will remember with this one single flowchart. So like that, you will create your own notes. All right, so I'll stop it here. Let's connect tomorrow. If you don't have any questions, then we'll wrap up.
Thank you.
Thank you all. Take care.